Ok, espero que ya estén con su español totalmente dominado a 2 días del Congreso. Well, welcome everybody, good afternoon, and we're about to start the plenary. I'm gonna read a brief and probably unfair summary of our plenaries. Professor Kristin Persson. Kristin Persson is a Daniel M. Taleb Distinguished Professor in Engineering at the University of California, Berkeley. She is the director of the Molecular Foundry, a user facility of Lawrence Berkeley National Laboratory, and a faculty senior scientist at the same lab. She is the director and co-founder of the Materials Project, which is one of the most visible of the Materials Genome Initiative, funded programs attracting more than 250,000 users worldwide, with thousands of unique users accessing the site every day. She's a leader in the MGI community and applies modeling and data-driven methodologies to the innovation of materials for energy storage and production. She serves on the advisory board of NanoHub, Fairmath, and she is the appointed MGI ambassador for the Minerals and Materials Society. She has received the DOE Secretary of Energy's Achievement Award, the TMS Faculty Early Career Award, the 2020 Falling Walls Science and Innovation Management Award, the LBNL Directors Award for Exceptional Scientific Achievement, and she is an APS and Kavli Fellow. She holds several patents in the clean energy space and is among the world's 1% most cited researchers. She has co-authored more than 230 peer-reviewed publications. She has an index of 84. Persson obtained her PhD in theoretical physics at the Royal Institute of Technology in Stockholm, Sweden in 2001. She's a terrific scientist, and you will see that pretty soon. So go ahead, Professor Persson.
Thank you so much for that very kind introduction and for inviting me to this wonderful conference. It's great to be back in Mexico and Cancun. I hope with this talk that I excite you about the role of data as an innovation multiplier in material science. So 4 paradigms of science have been proposed. If we start out with the first paradigm, which is empirical science, and the early days of science when we would look around in nature and observe and see patterns. As those patterns become more and more systematic and we use mathematics, we can cast those observations into equations, such as Maxwell's equations or the Schrödinger equation, which helps us to describe the behavior of nature. With the advent of computers, so now we're in the sort of coming in our later centuries, the advent of computers now allows us to solve those equations of science more rapidly and robustly, and without having to make observations, we can predict how nature behaves. That's the third paradigm of science. And we are proposing that material science is entering the fourth paradigm, where in some instances we can produce enough data, either by simulations or by experiments, or both, that we can use just the data alone to use data-driven machine learning algorithms to predict the behavior of matter. However, again, it is data-driven. So the strength of those models will be highly dependent on the amount of data, the curation of that data, the provenance of that data, and the accuracy of that data, and the systematics. So I hope to show you where I think we are in this respect, what we need to do better, where the pitfalls are, and some examples of data-driven materials design. So if I were to go back, of data being so important, when I was a graduate student back in Stockholm in the mid-90s, and somebody asked me how to find data from materials, I would have gone to those beautiful old books. And I bet you that most of the students here in the audience haven't heard of them. How many people have heard of these books? Oh, actually, that's pretty good. That's much better than the last talk I gave. Fantastic. You guys are great. So they're wonderful, right? They have really highly curated data. People went to a lot of trouble to make sure that the data that got published in these books were highly vetted, so we could trust them. But in the end, looking to the inorganic world, there are something in the order of 100,000 to 200,000 unique compounds, unique materials in the world, if you don't count solid solutions and those kinds of things. And if you actually scour the literature for very fundamental materials properties, including Landauton-Bernstein, you get about 200 elastic tensors. And they're mostly for cubic systems. That's nothing, right? 200 elastic tensors, considering how long material science has been an important science in the world. If you go to something slightly newer and more exciting, like, the superconductivity of materials, the TC of superconductors you can find for about 1,000 materials. And that's because if you actually find something with a high TC, you get a high impact publication. But if you measure just a random elastic tensors, I don't know where you would publish that today. And if you go back to something, again, slightly more on the mundane sort of things, like dielectric tensors, you're again looking at the 300-400. And we have literally looked at this very systematically. So there isn't a lot of data out there in the open literature. I think there is. There might be many reasons for this, but I would argue that just data for itself has not been highly valued in our society, in our science. Data is only valued if it's tied directly to an innovation, finding, for example, a high TC superconductor. But if you just find a data point of an elastic tensor or dielectric tensor, and it isn't tied to an insight or a discovery, people say, like, well, I don't know if I care about that. But yet, if we're going to do data-driven science, if we want to benchmark our calculations, if we want to know how good those simulations are, the gold standard is that really good experimentally validated data point. So they are highly valued, but we haven't really put that value into it. And if you're going to do data-driven materials design and you have 200 elastic tensors, 100,000, 200,000 materials, there's no way you can tie elastic behavior of materials back to its crystal structure and chemistry. So how can we do better? Well, so the literature, the open literature isn't going to help us. But again, going back to the early days of the mid-90s, something started to happen then. There was a paradigm change in terms of the ability to calculate materials properties faster than we could measure them, especially if you have to make a single crystal in order to measure that property accurately, like, for example, the elastic tensor. So density functional theory could be cast in such a way that we could access high-performance computing clusters and calculate not all, but a fair few of materials properties very, very rapidly and accurately. So this is where we are entering basically the third paradigm, right? We have an ability to calculate using the Schrödinger equation, materials properties, in a robust and systematic manner. Well, it didn't happen overnight. So again, taking the mid-90s, I was a graduate student in Stockholm. I spent an entire year calculating the phonon dispersion curves of tungsten. So charting out the vibrational behavior of one element. That took 1 year. Because in those days, we have to parameterize pseudopotentials. We had to parallelize a linear response code on our supercomputing center. And our computers were nearly as good as today. But if you look at the materials project today, in 2023, so about 20 years later, we now have over 150,000, way beyond elements, calculated materials with millions of associated properties. And just to take phonon dispersion curves as one example, I think we have around 3,000, and well beyond elements again. That is a paradigm change. And that is starting to enable this data-driven material science that we hope to accelerate materials design to solve some of our societal problems that honestly we're a bit too late already with. We're going to try to do what we can, right? So phonon dispersion curves, Courbet diagrams, elastic tensors, piezoelectric tensors, all of these can now be calculated faster than we can measure them, and we can add orders of magnitude of data to the open literature and try to sort of accelerate it that way. The idea, of course, is to do materials design more in an accelerated fashion. Traditionally, we call what we have done Edisonian approach, where people come up with an idea. If I want to come up with a new battery material or a new sensor material, I may have an idea of where to go, what kind of crystal structures. I like perovskites, so I'm going to go to a perovskite system. I may know what kind of elements I want to put in there, and I try to make it, and then I characterize it, and I test it for whatever properties I was looking for, and I keep iterating. That's the Edisonian approach, and it was baptized after Edison because that's indeed what he did when he tried to identify the filament for his new invention, the light bulb. And he ordered over 3,000 materials from all over the world and tested them sequentially. Interestingly, he was completely convinced that this had to be found in the carbon family. So you could argue that he was limited, both his intuition, or today we'd probably call it prejudice, that this had to be, he knew the chemistry of the world so well that it had to be a carbon-based material. So he identified after 3 years a bamboo carbon, and he was happy with that. And only a decade later, a Hungarian group discovered tungsten as being a better material, better filament for the light bulb. So can we do better today? Well, the idea is, of course, that we can pre-filter now using computations, using computers. We can calculate materials properties. We can calculate some of the properties that Edison would look for example, in his. And we can tie those back to crystal structures and chemistries. We can filter by pure filtering which kind of materials would be more likely to fill the metrics we're looking for. That's one aspect of it. We can learn from where our intuition tells us to go, or our prejudice tells us to go, or maybe there are pockets where we didn't think we should be going, but we can. And the computer, being fairly agnostic about chemistry, doesn't care, would tell us, yes, there's actually something you've forgotten over here. So there are multiple levels of usage to this that we can pre-filter, we can learn, we can use data-driven models, and we can hopefully work together with our experimental teams to learn what we can do better as well. Perfect. We know that there are pitfalls in all of our theories, and working closely together with experimentalists is really the way to go going forward. And there should be a feedback loop here, and I'll hope to show it. Of course, we would like to become Tony Stark in the Iron Man. If you remember the first movie, where I think he has Jarvis render the periodic table, cool-sounding elements, like dysprosium and cerium, and he synthesizes it in his hands, and then he tests this for biological compatibility in about 30 seconds. We're not quite at Tony Stark yet. But that is the idea. I want Jarvis, too, in my lab. Not Tony Stark so much. I think Jarvis is much cooler. OK, so you might ask, is this real? Is he just he's just selling us on a dream? Well, it is real, but that doesn't mean that it is not hard work as well. So since we started doing this, and the first project we did that convinced me that it could be done was in 2006, and it was actually a company. It was not the Department of Energy or the National Science Foundation. It was a company that came to us and asked, hey, I've heard you guys can do computations. And I wonder, can you find if there's any better cathode material than manganese dioxide for these little alkaline batteries that pretty much sit in every device we have, right, including this one? So this is when we had never done this before at that point. We had never spit out these calculations, filtering for voltage and capacity and all the other things, stability that matter for batteries. But we thought, OK, sure, we can do this, right? So we asked for $1 million in a year and a half to do it. And they paid it, and they also gave us access to a really large computing cluster that was in there that they owned. And we filtered over 100,000 materials, 10,000 by actual DFT calculation, and the other 90,000 by doing this data-driven sort of exploration that was faster than doing the DFT. And in the end, came up with a list of 200 materials that we thought had a good chance of beating manganese dioxide, which was actually really, really difficult, not on the energy metrics, but on the stability metrics. Surviving at pH 15, there's not that many materials left in the periodic table. So that was the first time. And after that, these are just some examples of materials that in-house, people that I either fund in the materials project or that are associated with us that have predictive materials from DFT calculations and data-driven methods alone, have acceptance tests and methods, which we've also learned the hard way, that if you don't look at the data, you're going to release. Occasionally, there are really horrible bugs that will not just be a bad data point in itself, but because we're building aggregated data sets, we're building phase diagrams. If you have one bad data point, you can actually destroy a whole phase diagram. Again, we learned that the hard way. There was a particular nickel oxide that was overstabilized because of the way the density functional theory works. And every time we calculate that nickel peroxide, it was so stable, artificially too stable, that it threw every other nickel oxide, including the ternaries and the quaternaries, off the hulls, which was terrifying. So all of these things have to be learned. Failures have to be learned. Mistakes have to be learned and kept track of so that we do better every single other time that we calculate something. We've also, you may think that we started in 2011 and we're just building new data into the materials project, and we do that, but we also recompute things all the time because we realize that density functional theory is also a moving target. We're also getting better at solving the Schrödinger equation. So we have recomputed the data that you see in the materials project today many times already. And we have a deprecation process that moves the old data back. You can still access it through the API, but what we're serving normally through the website and through just the default calls are the best possible data that we today have gauged that we can reproduce with high throughput methods. So this is a lot of work. If a student comes to me and say, hey, Kristin, they always tell you, I want to do machine learning. So, okay, I'll tell you, I want to do machine learning because that's the hottest things today in material science. And I said, fantastic, you're going to spend first amount of time learning our code infrastructure. And then you're going to design a workflow code that's going to produce the data so that you can actually do machine learning, because you're going to need some data for that machine learning model. And then you're going to test that on the available gold standard experimental data that exists in the community. So you're going to have to scour the literature or write a script, and all the, ferroelectric response constants that you're looking for, or something like that. And you're going to have to benchmark that against your workflow. And which usually takes something between 6 months to a year, then you can go to town and calculate what you're interested in across chemistries and structures and get new data and figure out where are the cool materials, filter it, but all data-driven models help you build out the whole world of hundreds of thousands of inorganic systems and scour it more quickly than we can do with DFT. And then, of course, since students today, they also go on Twitter, I suppose it's X now, and they tweet and they get excited and share it with the world. So that's the process. Okay, so hopefully I've given you a sense of what's involved, and I'm going to give you a few examples of actual design of new materials that we've done in-house, where we work with experimentalists to show that this is real and we can bring value to the community, and I'll also highlight where I think the bottlenecks are today. So we talked about the paradigms of science, and this was the old paradigm, right? You had some idea, this is your brain working on something with your experience, saying, I'm going to synthesize this material, and then I characterize it, and maybe I didn't get exactly what I wanted, and I keep testing, I keep iterating, and then we added the third paradigm of science where we can compute materials properties, and now maybe we can filter, not go for just my intuition, and we're adding to my intuition, my experience, we're adding this other tool in the toolbox. Now filter out bad ideas and focus on the ones that are more likely to be useful. And this is a great addition to our paradigms. But I also wanted to highlight that unless these other aspects are as fast, turnaround, and automatic feedback as your calculations, you're still going to have some slow steps in your loop. And that's going to clog you down. And I would like to keep that in mind when I give these examples. So we've made some new materials within the materials project. So this is just our team working with experimentalists, depending on materials we're looking for. We've done it for carbon capture, magnetocalorics, thermoelectrics, photocatalysts, and piezoelectrics. And I'm going to take those two and show from the beginning to end how we designed novel materials or discovered. So the first example is from the Joint Center of Artificial Photosynthesis that then became LISA in the United States, one of the big hubs, well-funded. We were not part of it in the beginning because they started right about when the materials project was being born. But in a few years, they sort of learned about our capability, and they came to us and said, can you help us? We really need to find better photocatalysts, materials that can absorb the sunlight and excite an electron hole pair and split water to make sustainable fuels, carbon neutral fuels for our planet. And we took a look at what existed then as known photocatalysts. And in this particular case, we were looking for a photoanode, because that seemed a little harder than the cathode ones. We were looking for holes being produced that had the right kind of energy to split water and produce oxygen. So for that, we needed a valence band maximum with the right kind of energy, for those holes that is close to the oxygen evolution potential. We needed a band gap that was amenable to absorbing very efficiently the sunlight, so that's around 1 to 2 eV. And the third criteria, which is usually not considered, we also need something that's stable in water under the operating conditions of your device. You're going to split water, right? So you're going to need to be in water. And usually you want either acid or alkaline pH because you have higher efficiency of your device operation under those conditions. The sort of garden variety semiconductors that people have looked at did really, really well on criteria number 1. They just had a perfect position or a very good position of that valence band maximum. They did okay on the band gap, being in around the sort of, but the last one being stable under pH 13, and we decided to go for the alkaline rather than the acidic side, because the acidic side is even worse. It's hard to find materials that are very stable under pH 1 or 0. So pH 13 was more benign, but still none of these guys were stable. And by stable, I mean either they corrode catastrophically, they just dissolve, or they dissolve enough and then they form a passivation layer of some oxide or something on top of them. And because we're looking for a catalyst material, something that's going to do something, and I want to highlight again that these first tiers are all something you can do in minutes. You don't have to do a single calculation yourself. So we were very fortunate that in JCAP we had a partner down at Caltech, John Gregoire, who had this inkjet printing thin film machine to synthesize materials. So he can make materials pretty rapidly. So he took those 34 materials. They were actually known phases. None of them were new, completely new. And he was able to make 17 of them, synthesized through this combi approach. And then he tested them directly for activity, for photocatalytic performance. And 16 out of them, of those, the ones he was able to make, actually showed activity of varying degrees. So you can see here that the radius of the ring tells you about the photocurrent. So the bigger the circle, the better the material. This is pretty good, right? 16 out of 17 in terms of hit rate. Yes, he wasn't able to make 34. He was able to make 17 of them. But out of those, DFT had given him basically the right number. If you were to just throw dart arrows at this, or the periodic table, you were unlikely to have this kind of hit rate. We also learned nicely that the photocurrent very nicely agreed or showed us that the electronic states at the valence band and the conduction band correlated with certain chemistries in this chromium, manganese, and vanadium space. So having low-lying empty vanadium D bands and not having oxygen P bands at the very top of your valence band correlated well with a good photocurrent, and we understand why. So that was the first example, and it was highly accelerated by having this nice high-throughput combi approach, one shot being able to make all these materials, or at least a good chunk of them. So I'll now show you a very different example. So piezoelectric materials, they appear in sensors in the world. Not a huge amount of material, and again, probably not something you think about saving the world in terms of energy efficiency. But the most used piezoelectric material is PZT, and it contains lead. And Europe just banned lead being part of any industrial process. But they've given exception to PCT because we don't have a good replacement for that material. And even though it's very small amounts, it's in a lot of devices. So it goes into our waste stream in a lot of places. So we decided to, okay, maybe we can do better here. So we started by designing a workflow for calculating the piezoelectric tensor, benchmarking against what we could find in the literature. And here we're only looking at 50 fully characterized, measured piezoelectric tensors in the open literature. And after that, we just had to release our workflow and do the best we could. We have disseminated this data to the world. We keep on chugging, so now we have 1,000 tensors. In the early days, when we had about 1,000, we decided to filter out and see which ones could we show that maybe could be a candidate, maybe. This is the first data set that we had, and we filtered it just like we did for the photocatalytic material. And we found an interesting material, we thought, a strontium hafnium oxide that had never been made before. It had a high piezoelectric response in one direction, and we thought, okay, maybe this is cool. So what do you do when you have a completely new material that falls out of the funnel and just has a high performance metric? Well, what we typically do is we go back into the materials project and we enter this, kind of like the Google of materials here. You enter your stoichiometry, and out comes a list of materials that have that stoichiometry. Now, the ones with the stars are the ones that have been made. They're existing materials in nature or synthetically. The one we're actually targeting is the one down here. It's the only one that's polar, the only one that's going to have a piezoelectric response, and it's number 1, 2, 3, 4, 5, 6 in order in terms of stability. It's 30 MeV above the hull, which in itself is not a bad number, but the fact that it competes with 500 materials, 3 of which already have been made, is very bad news indeed. And normally when we get to this stage, me and my experimentalist partners, we go like, nah, this is not where we're going. We're going usually for low-hanging fruit, things like materials that have been made but have a new unidentified property to it, so that we have a synthesis recipe that we can fall back on. We would normally have given up at this point, but we had some very brave people at NREL, one of the labs in the US, Dave Ginley and Lauren Garton, who said, no, this is awesome. This is a challenge. We want to try to. So this is the guy that we were trying to make. We used an old algorithm from Zur and McGill from 1984 to synthesize, to design a substrate for thin film synthesis that would penalize other more low-lying phases of strontium hafnium oxide and promote by elastic strain and by the topology that particular polymorph. Just that algorithm, by the way, is now on the materials project. So if you are into thin film synthesis, you can use this and you can tune your own substrate. We made a particular one. It was a niobium-doped strontium titanate substrate. And after 2 years of making the substrate, different kinds of synthesis conditions, Lauren Garton was able to make this material go to SLAC and characterize it and show definitively that, yes, indeed, this very thin film is that particular strontium hafnium oxide and not any of the other more low-lying, more stable versions of it, which was a hero attempt, in my opinion. 2 years. And you can compare it to the calculation, which probably took in the order of minutes to calculate the piezoelectric tensor of this material. So hopefully that, I wouldn't recommend this normally, but it is a very good example of how hard it can be to make a completely new material. And we do have examples like this. This is a predicted material. It's a magnesium cathode material. It's a double substitution on an existing crystal structure. It's in the materials project. About it. Nobody's ever wanted to make it because there is a synthesis recipe. Lauren isn't into cathode material, so we couldn't entice her to do it. But it has one of the lowest diffusion barriers we've ever seen. So if it is real, it would be a very cool discovery or innovation. But yes, this is one of those bottlenecks, again, in terms of synthesis and characterization. So synthesis. Synthesis recipes is a big deal because synthesis is inherently a data-driven science. It does not have an equation associated with it. We have an idea that Synthesis is driven both by thermodynamics as well as kinetics, and it's very much dependent on the method, which one dominates. So we really need a lot of data to understand synthesis. That's why we probably go to people that have a lot of experience when it comes to synthesis. The Bob Cava groups of the world, where people have done synthesis for many, many years, and they have all those examples in their brain about how to tune the parameters to get exactly the right way to make a material. And if you think about it, they only publish successes, right? And if you know anything about machine learning, you know that that is a really bad data set to train your machine learning algorithm on if you only have the successes. You need the failures too, but as a society, as a community, we don't publish failures. And that is a real aspect of what we need to do better in the future. We need to publish failures, because if we're going to do data-driven synthesis exploration, we need to know where things go wrong as well as things go right. We've actually tried, in the early days, we tried to make students put into notebooks, like when it didn't work. And even though they understand how important it is, they go, please don't make me revisit that. I just want to move on. I just want to make the material. Let just me to go into the lab again and try again. That's what they want to do. So how do we do better with synthesis? Well, again, going back to that energy above hull, ICSD, the International Crystal Structure Database, which plots, here's for oxides, the energy above hull of all oxides that have been made in the world, or that is in the ICSD. As you can see, it rapidly falls off. My cutoff at 100 MeV per atom, which is something that we calculate, that's basin, right? I get 80% of all known realized oxides. Okay, you could say like, well, that's a decent metric, right? Yeah, I'm going to lose 20%. Those are, you know, the ones here, and I'm sorry to say that I'm not going to get them. But it's not so bad. 80% is fine. It doesn't, if I get something that's below here, there's no guarantee that you can make that material, but there's a reasonable chance for it. Okay, that's oxides, but if we now look at other chemistries, this is the oxide line up here. You put your metric at 100 MeV, you get about 80%. But if you go to nitrides, that number is only 50%. So suddenly we realize that stability or realizability, synthesizability is chemistry. Nitrides are clearly much more resistant or robust against metastability than oxides are. And we can discuss why that is, but clearly from a computational point of view, we need to be more generous in the nitride space than we are in the oxide space. So there are probably better metrics out there for when something is synthesizable, when we can send our experimental counterparts into the lab and hope that they can make something. So we started thinking about the process of synthesis. If you want to make a particular polymorph, a particular crystal structure, let's say in the tantalum nitride space, and you may be mixing, and this is from a paper, you may be mixing tantalum oxide and ammonia, and you heat that up. The first thing that's going to happen, well, you're going to break bonds, right? You're going to break up your precursors, and you're going to make something. So making something, kinetically, that could always be amorphous stuff, right? Kinetically, your amorphous state is always possible. But what about the thermodynamics of your amorphous state? So we can actually calculate a proxy for the amorphous state using computational workflows. It's not perfect, because we all know that amorphous materials depend on how you made it. There are many different versions of them. But we can take different kinds of snapshots and take an average and realize that, well, we're probably above the actual energy of the amorphous state, because nature is much better at exploring all those different variations than we are, but we can get an estimate. And if you calculate the enthalpy of the amorphous state, we can also hypothesize or postulate that the entropy of that state is going to be higher than any crystalline polymorph because of that disorder, that configurational disorder that's much larger than any crystalline material. So the slope of Gibbs free with temperature is going to be higher than all the polymorphs. So let's now look at this graph here, where polymorph B and C starts out with an enthalpy of those polymorphs that's lower than the amorphous state. They have a window of thermodynamic stability compared to the amorphous state. But polymorph A, that starts out with an enthalpy that's higher than the amorphous state, has no window of thermodynamic driving force to form at all. So if the precursors are falling apart, they can make the amorphous state, there's no driving force for it to make polymorph A. If you're within this window here, there are driving forces to make polymorph B and C. So we hypothesize that a upper limit, a rigorous upper limit, thermodynamic upper limit for synthesizability is set by the enthalpy of the analogous amorphous state of the material. So let's test that. We took 44 atoms, oxides, nitrides, carbides, and calculated the amorphous state, the amorphous enthalpy for these different systems. And you have to calculate once for every single different chemistry. And also, if you do it at different pressures, that also has to be a different one. But this is just ambient pressure. And these are set by all these bars. And as you can see, they vary quite a bit in energy above the ground state. So anything from like 100 MeV up to almost 1 eV. So very, very variable. And the filled circles are materials that have been made and that survive at ambient pressure. So they're real materials. And the empty circles are materials that either have never been seen, they're in the materials project, they're hypothetical materials, or they have been made at high pressure, but once we bring them down to ambient pressure, they amorphosize. So they're not stable at ambient pressure. And as you can see, there's not a single system, even though this amorphous limit varies quite a bit, that violates this rule. So we do believe that it's real. And this gives us some chemistry as well. If you compare the amorphous limit of boron oxide and boron nitride, you see that the boron oxide has a fairly low amorphous energy, enthalpy. That means that you have a low window of metastability, right? Because you can't make that many polymorphs. They all have to be lower than that enthalpy in order to be realizable at any temperature. And it's also set by the fact that boron oxide doesn't really care how these little tetrahedra are organized, right? It's pretty happy being amorphous. But if you take boron nitride, which has these highly directional covalent bonds, then you're going to deal with a much higher amorphous energy because it hates being amorphous. So very high enthalpy of formation. And that means, in turn, that you have a much larger window of opportunity for metastable materials to form, which is great, right? That's what we like. We like to have some playground in order to make these different kinds of structures. So now, of course, you know what the skyscraper is. There's a reason we have Nobel Prizes in carbon, graphene and the buckyball, right? Because we have this enormous enthalpy of formation of the amorphous state, which gives us this wide window of possible metastable carbon structures. So this is a handle for us to understand where are the opportunities and which materials we shouldn't even try to make because they are way outside of the synthesizability limit. So this is another tool in our toolbox in order to guide synthesis, but it's still not enough because it's still just thermodynamics. We do call it the synthesizability skyline because the first author on the paper came from Chicago. Skyline. All right, so, okay, going back to the closing of the loop, this is the loop that we have, and we highlighted that these two steps here can be slow, and we need to do better. What do we do in our current synthesis? Well, it's pretty slow iteration. If I come up with a good material, I go to my counterpart group, I ask them to try to make it. We've highlighted that negative results are only collected in the minds of individuals, the experience of groups. Provenance is usually incomplete, and the data cannot be leveraged by the community, saved anywhere except in the minds of those groups and the experience. So automation is really, truly the great enabler. That's what happened to us, right? That's what we did by automating density functional theory calculations and save failures to the lessons learned, to the old data, to all the trajectories. We've saved it all. And I'm not saying we should save it all, because that's a big problem when it comes to some characterization techniques. But we have saved a lot, and it has really helped us with this ability to map out the landscape of materials and do the same for synthesis and characterization. If you automate things, you don't have to tell your graduate students to enter it into Notebook anymore. You will get the negative results. You will get the provenance automatically collected. And now you can also give the data to the greater community so we together can accelerate materials design. So this is the future, if we can automate all of it. And I'm putting these little infrastructure boxes everywhere because it is going to need a lot of software infrastructure. And your students and your postdocs are going to have to become savvy in Python and APIs and all of that stuff, because it's needed to make this work seamlessly without people moving PowerPoint slides between each other. And I really want to give a shout out to the SADA group at Berkeley Lab that have partnered and built this wonderful A-lab that literally is a bunch of robots going around and doing exactly what a graduate student would do. They take precursors, they mix them, they grind them up, they put it into furnaces, they take them out of the furnace, they put it into the XRD, they do a rapid scan with the XRD, then they use machine learning algorithms to figure out where the accurate XRD sample from, so I can learn more and specifically identify what we made. It is a beautiful example of automated synthesis and characterization. It talks directly to the materials project. So here's the first run. When the A-lab came online, it became self-aware. No, not really. Not too many people seen Terminator. Oh, never mind. When the A-lab came online, we gave them 58 new compounds, completely new compounds, so the same as that strontium hafnium oxide. And we asked it to make all of them. And the A-lab iterates by itself. So it's not students who come in and tell them, you know, fix something, do this, do constant chemical potential. It iterates and it learns what it should do differently. So in 1 month, it made 41 completely new compounds. That's pretty awesome, isn't it? And now imagine that all of those failures and successes are also saved. So we can learn from it, and we can do even better. So this is the future, and I'm very excited about it. My very last 3 minutes, I'll be talking about what the Materials Project does for the community and how we try to give this data, what we produce, to everybody so we all can do better. We've talked about how machine learning is what everybody wants to do. I like it to this red Ferrari, so my students want to drive the red Ferrari, and I tell them you're going to have to produce the fuel, and the fuel is the data. And your machine learning algorithm is only going to be as good as the data you train it on. It is not going to reinvent something by itself, and if it does, I hate to tell you, it hallucinates, and it's usually wrong. It's very bad. So the Materials Project is trying to add this data in any way we can to the community. We've been around now for 12 years. We recently redid our website, our front pages, with a completely new infrastructure, which allows us to more rapidly move data and algorithms to the community. So as some examples, here are 3 new apps that came online in the last year. One is the Synthesis Explorer that uses synthesis recipes that have been learned by natural language processing from the literature. That was contributed by the SADA and Olivetti groups. They had a separate grant to do that. But again, usually, right? These are successful synthesis recipes, but it's easier to look up now than to find it yourself. The Catalysis app, which comes from the Facebook Meta collaboration. So again, an outside contributor to the material. And the last one, the Moth Explorer, which comes from one dedicated student from Northwestern who spent his entire PhD calculating metal organic frameworks and then donated the entire data set to the Materials Project. So hopefully this is something we can do better as a community to work together, that when we have used as much as we think we can use it, we see what the rest of the world can do with it. The Materials Project itself, what we do in-house is we focus very much on the properties of materials rather than just crystal structures, because it's really the correlation properties and crystal structure and chemistry that allows us to do this accelerated learning. And where do we look for materials with the perfect properties? If we only do crystal structures, we can't do that. So we put a lot of our effort into all these that we've calculated throughout the years, rather than building out structure space. And people come to the Materials Project. We have a very functioning API. We deliver millions of data points to the world every single day, somewhere in the order to 5 to 10 million data points. And sometimes it's up to spikes. So 45 occasionally gone. In the early days, before we learned how to do this effectively, the whole website went down because someone didn't ask for 45 million records. So we try to do this now very, very sustainably and making sure that nothing gets throttled. When people use our data, most of them cite us. Every day, 4 papers are published citing use of the Materials Project in one form or another. Data, algorithms, or both. And 2 of those in the last year. This is the ramp up of machine learning, are citing it for machine learning purposes. That's how big this is becoming. This is the new fourth paradigm of science, machine learning, and data-driven methods. I'll give two brief examples, and I'm out of time, so I'm going to do this very quickly. Of two with us, they used our elastic tensors, in this case, to design not super hard materials. They made them, and they characterized them, and this is a nice publication in JACS. We have nothing data, and that was an innovation multiplier for that group. Secondly, this is another group that used the band gaps and the elastic tensors to phosphor materials. Data, it accelerated the look for new materials, and then they had a nice publication in Nature Communications which showed their synthesis and characterization. Machine learning interatomic potentials are clearly the new kids on the block. A lot of people are very excited about this. This is basically mimicking the Schrödinger equation for a fraction of the cost, so we can long simulations. And starting in 2018, going to today, you can see the ramp up of all of these different machine learning potentials. They're all trained on the materials project because we've saved every single relaxation that we ever did over years. And that's trajectories showing how materials, forces and energies respond, is now training all of these machine learning interatomic potentials. Obviously, there are false. I've mentioned a few of them. If we don't have negative results, we're going to have very bad data. We are now machine learning everything from transition states to defects to phase diagrams, and we do have to be critical because, again, the machine learning algorithms are only as good as the underlying data. And there are dragons out there. If you go outside of your training set, like any good trained algorithm, it will give you an answer, but it may be a complete hallucination. So keeping checks and balances in place, having experiments and DFT as stops and checks for that data is highly important. Building in checks outside my training data. Can I build in physical boundaries where the data should exist? Can I have equivariance to show that a tensor should behave in certain ways? There are ways of making it better, but we do need to be cautious. With that, I think I'm just going to show that we have a lot of users, over close to 400,000 today, being accessed all over the world. Very excited about it, especially for people who don't have access to the same kind of journal licenses that we take for granted in the United States. And we're adopted as this last one, or the last to come one, of a lot of very highly curated data in the US called the Pure Data Resources. From the atmospheric data to the particle physics group, we're now the only one in the material sciences supported by DOE. And this is my group, and the 4 people that are software developers in my group that all have a background in science, but have decided to pivot to software engineering, retaining their domain expertise. And with that, I'm very happy to take questions, and thank you so much for your attention.
Thank you. A fantastic talk. So, do you have any questions? Don't be shy. Okay, that one, and then that one.
Well, very spectacular talk. Well, my name is Lucia from Institute of Physics in Mexico City. So, based on the results that you presented, you can see that it's a field that is evolving very rapidly. You benefit from all the data that everyone could contribute to this. But there is a key thing that just comes to mind is how beneficial will be to have also, for example, properties as a function of temperature. Does it make sense to even go in that direction? Can you elaborate, please?
Absolutely.
Thanks.
You know, every single proposal we've written for the materials project have included temperature-dependent properties, especially phase diagrams. I'm just going to admit that it's in automated fashion. We've tried to build a robust automatic cluster experiment for the last 10 years that can do this without a lot of manual intervention. And it's just really difficult if you are going for any lattice, any material, any system. So we are working on it, but it's probably going to be limited to certain systems to begin with. But you're absolutely correct. Of course, we want temperature-dependent properties in there. And we'd love to partner with anyone who wants to help.
Next question.
Yes, hi. Congratulations. I didn't know, I knew the project. I mean, I'm from Panama and started back in 10 years ago using this, and it's amazing, mind-boggling. I knew it was important, but now I see the importance that it has, so congratulations. Thank you so much. My question is that I know when the page changed, and I'm not able to access data anymore, and I'm not sure, I mean the raw data, when we do the XRD or whatever, and I was like, oh my God, now I can access the data. So, and there are a few things. My question is there is tutorials or there is a way of getting to get the maximum from this website, which is amazing.
Oh,
and
yeah.
Thank you so much.
No, it makes my day to hear that. Website. We used to give a workshop, a yearly workshop, and during the pandemic, we moved it virtually. The last 2 years, because it has so much development of the infrastructure, we haven't been able to do it, but I would love to do it again. It highly relies on my group and my people to do it, so when they're a little tired, I said, like, okay, let's not do it this year. But that is one, and those tutorials are online from the last year, which I think is 2020 was the last time we gave it. So those are probably a good resource. We save everything. So if there's something you can't access that you used to be able to do, for example, we have moved some things from the API to longer access storage because we actually pay for our API these days. We moved everything to the cloud, to AWS, to be available 24/7. We used to reside at the High Performance Computing Center at Lawrence Berkeley Lab, which was free, but it also meant that we were every time they went down or maintenance or something, and that just wasn't sustainable with the whole world relying on our data. So we are paying for it now, which means that we serve most of the data to the API, but if there's some raw data that you want, we can still give it to you. You just have to contact us. But yes, tutorials online, documentation online. We will bring the workshop back. And third, if none of those work,
Go ahead.
Yeah. Can I ask the question?
Yeah.
Okay, thank you. Thank you very much for this remarkable contribution to our community. I have one remark which will lead then to a question. First, I say I totally agree with you regarding negative results which are not reported. And I would also add that maybe we should get the habit of also reporting the limitations of our approach. And this is something to reporting on negative results. And this leads me to my question regarding limitation. I'm also a theoretician, but more level than to material level, so I would be more of a user of this kind of database. And without knowing that as I'm a user of the output, not all output will be equivalent. All output will have the same quality. And this, especially in DFT calculation, will depend a lot on the approximations which are being made. For example, if you're ignoring sin latitude, then some of the data are going to be maybe a little bit less reliable than others. And when you are working like me at device level, this can change everything. So I wonder if this is something which you're looking into to implement, for example, a way for the users to curate the data based on some specific approximations. And I believe it would be very useful for people like me who are not really material scientists,
that's
se.
Absolutely true. The idea is everybody should be able to use this, and we do recognize the vast majority of our users are not DFT experts. That's the whole point, making this available in a way that they can use it with some amount of information on when is it accurate without having their friendly DFT modeler. So we do try to make that, like we put warnings, like this isn't a very good number, but it is an estimate. So for example, the band gaps come with a large warning label on them because we know they're underestimated. we do better? Absolutely. There is a vast amount of literature on like when certain DFT function will fail and not fail, and we try to do as best as we can. We actually did implement at some point, like for a couple of years, we had like a box for users to enter on something wrong, or if they, wanted to, very pathetic. I would enter, and at some point I go like, oh, let's just get it done. And I've come to realize that we're pretty shy as a community. We're putting our, so if you guys bring it back, you're gonna have to promise to put some stuff in there. Excellent.
So there is another question.
Thank you, congratulations. It's very talk, and it's very talk, and for me it's amazing how statistical mechanics, quantum physics, dynamics, everything is mixed together to prepare these new materials. My question is a little bit about the ethics. What will happen in the future? Because materials that do not exist right now, and in a way it can be like plastics, no? That we did a lot of plastics, and then there is a lot of pollution, and we don't know what to do.
Yeah.
And in this sense, there are some prediction also about what is this manipulation bring.
Yeah, no, that's a good point too. I think we've all become very aware that just because some material fits the metrics of a particular device or a commercialization sort of strategy doesn't necessarily mean we want to introduce it into our community. So being aware of the impact on our society, on our materials making is important. It's very hard for us to calculate what that would be. We occasionally partner with people who tech economic models to look into these kinds of aspects, like what would the impact be of these materials if they were to come online and if they were to become successful. But I think we all have to ask ourselves that when we participate in materials innovation. Is this something I want to bring to the world?